In example 3 here, we are finding a volume of the solid region that's under the graph of z equal x squared plus y squared. That's this paraboloid here, circular paraboloid, above the xy plane, but inside the cylinder, x minus 1 squared plus y squared equals 1. That is this cylinder in gray. So we only want the volume out here that's underneath that cylinder, underneath the paraboloid, but inside the cylinder. So volume is just going to be the double integral over our region, R, of the function f of xy dA. Now what we notice here is that this function is nice in polar coordinates. It's just r squared. And then this cylinder is actually nice in polar coordinates too. So we should set this double integral up in polar coordinates. So first we want to sketch our domain here. And that is going to be what's inside that cylinder. That's going to be a circle in the xy plane. So we've got a y-axis here. And let's see, this gets shifted in the x direction. So an x-axis here. So this is x squared plus y squared equals 1, the unit circle, and then it's shifted 1 to the right because of the x minus 1. So that circle is going to look like this, where it goes up to 1, down to negative 1, and then this hits over at 2. So let's just set this up in rectangular coordinates just to see how messy it is, to convince us that, oh yeah, we really do want to do this in polar coordinates. So let's say that we want to integrate first here on a vertical segment. So from the bottom of the circle to the top of the circle here. So that'll be a y integral, and then we'll sweep left to right. So we're going to do integral, integral, and then our f of xy, x squared plus y squared. And then we're going to set up dy dx. So to do the y integral, we need the endpoints of that vertical segment. That means we need to solve this relationship for y. So if you bring the x minus 1 squared over as a negative and take square roots, this top one is going to be y equals positive square root 1 minus x minus 1 squared. So I just solved that equation for y. And then down here, that's going to be the negative square root on the bottom. So negative square root 1 minus x minus 1 squared. So those are going to be our y limits of integration. So our lower limit of integration, y is negative square root 1 minus x minus 1 squared. And then up top, positive square root 1 minus x minus 1 squared. And then we want to let that segment sweep left to right here. So at the very leftmost side, we're at x equals 0. Very rightmost side, we're at x equal 2. So x will be 0 to 2. So we're going to, when we do our y integral, this will become x squared y cubed over 3. And then we're going to have to plug in these square roots, and it's going to get really messy. So, so this thing here, we don't really like that. That's, that's a frowny face. That looks like that's going to be a lot of work, messy, probably not a lot of satisfaction when we get done. So, okay, so what if we integrate with respect to r and theta? So this will now be integral x squared plus y squared is r squared. dA is r d theta. And then remember what you do here. You draw a general radial segment. So from the origin, we draw that radial segment. The endpoints give our limits of integration. So the inner endpoint is at r equals 0. The outer endpoint is on this circle, which has diameter 2. It's along the x-axis. That's going to be r equals 2 cosine theta. So if you change this expression to polar coordinates, you get r equals 2 cosine theta. So your y is r sine theta, square that. Your x is r cosine theta minus 1, square that out, solve for r, do some simplifying. So 0 to 2 cosine theta. And then let that radial segment sweep over the region, which is the whole circle. So it's going to start down here. That's at negative pi over 2. Sweeps over the region, 0 up to positive pi over 2. So negative pi over 2 to positive pi over 2 as it goes around. So theta, negative pi over 2 to positive pi over 2. And then this volume actually be symmetric across the x-axis here. So we could just do from 0 to pi over 2, find the volume that's above the upper half of that circle, and then double it, because it'll be the same as the volume below. So, well, let's keep going here and go ahead and evaluate. So this will be, let's change that to 2 integral 0 to pi over 2. And then we've got r squared times r is r cubed. So this will be integral 0 to 2 cosine theta. R cubed dr d theta. So we can't pull the r integral out because it's got a cosine theta in up there. So we just have to integrate. So this will be 2 integral 0 to pi over 2. Our antiderivative there is r to the 4th over 4. We are going to evaluate that from 0 to 2 cosine theta. And then integrate d theta. So this 1/4 we can pull out of the evaluation there to factor that out. So that'll be 2 divided by 4, so a 1/2 out in front. And then we've got integral 0 to pi over 2. And then we're plugging in 2 cosine theta. That gets a 4th power. Plug in 0 with a 4th power. The 0 doesn't give us anything, but we've got 2 cosine theta to the 4th power d theta. So we want to do 4th power on cosine, 4th power on 2. So this will be 1/2 out in front, integral 0 to pi over 2. And then 2 to the 4th is 16. And then we'll get a 4th power on cosine. So cosine 4 theta. And d theta. So then 2 goes into 16 8 times. And we can pull that 8 out in front. So this will be 8 integral 0 to pi over 2. And then when you got all even powers of sine or cosine, that's when you want to use your your half angle formulas. So we want to break that cosine 4th up into cosine squared theta, d theta. And then each one of those cosines will trade out. So let's see, we've got an 8 out in front, integral 0 to pi over 2. And then cosine squared theta is 1/2 times 1 plus cosine 2 theta. That's the half angle identity. And then we'll get another copy of that for this cosine squared. So 1/2, 1 plus cosine 2 theta. And let's see here, 2 and 2, 4 cancels into 8 and gives us a 2. So that is 2 integral 0 to pi over 2. And then let's multiply out what's left. So first terms, 1 times 1 is 1. Outer terms cosine 2 theta, inner terms cosine 2 theta, that's 2 cosine 2 theta. Last terms here, cosine squared 2 theta. And then d theta. We know how to integrate 1 and 2 cosine 2 theta. The cosine squared, we have to trade that out using another half angle identity. So equals to integral 0 to pi over 2. And then let's see, 1 and 2 cosine 2 theta. Those we leave. Plus, and then this will become 1/2 1 plus cosine 4 theta, because you double whatever angle is inside here. And then d theta. So that 1/2 can multiply in times each one of these guys. So we'll have 1/2 times 1 is 1/2 with the 1 out in front. This will be 2 integral 0 to pi over 2. 1 plus 1/2 is 3/2. 2 cosine 2 theta. And then 1/2 times cosine 4 theta. D theta. And now we know how to do our antiderivative here. So we are almost there. So we got that 2 out in front. Let's see, our antiderivative then of 3/2 is 3/2 theta. And then the antiderivative of 2 cosine 2 theta is sine 2 theta. Because you would differentiate sine 2 theta, get cosine 2 theta times the 2 on the inside. And then plus 1/2. And then the antiderivative of cosine 4 theta is going to be sine 4 theta. And then instead of multiplying by 4, you divide by 4. So we get a 1/4 out in front. So if you differentiated this, you get cosine 4 theta times 4, and then the 1/4 and 4 would cancel out, and you'd have your cosine 4 theta. And then we are evaluating there from 0 to pi over 2. So from there, it's just a plug-in. So a fair amount of work on that one, but still, I'll bet you anything it's going to be easier than using rectangular coordinates with all those square roots. So half angle formulas are your friend when you are working with polar coordinates.